Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel of everything I want to talk about science and math. And today we're in AP Chemistry, Unit 4, which is about reactions. So chemical reactions is this unit. I've already told my class most of this is review from honors. So we're really learning two things. So we're going to do this really fast and not spend a whole lot of time on the stuff we already know, but I did want to review it. I thought about just teaching you the new stuff. And I thought, nah, we better go over the old stuff that's in the standard. All right, so chemical or physical? Which one can be observed without changing the identity? Physical or chemical? Physical, yes. So the other one, of course, is chemical. When the identity changes, bonds are broken, bonds are formed, you get a new formula. Now this is a little bit new. There's something called intensive and extensive properties. Intensive properties do not depend on the amount. So copper chloride is blue whether you have 10 milliliters or 100 milliliters. So that would be intensive. Extensive properties, the volume of your sample, will depend on the amount. Now, back to chemical and physical changes. With physical changes, the identity does not change. And remember, the chemistry and math symbol for change or difference is the Greek letter delta. So that makes it easier to write. So this would be a phase change. Ice and steam are both H2O, something changing shape. A chemical reaction, and remember the abbreviation for reaction is RXN, the identity does change. So does the formula. So hydrogen gas and oxygen gas becoming water. That's a new thing. Chemical change, the formula changes versus physical change, it doesn't. All a review from honors, right? So the next thing is, well, what are the evidence of chemical change? So when we learned this in honors, I struck a match, and we looked at it, and we wrote down everything we were seeing. We saw that the stick changed colors. We noticed it had a smell, so there was a gas production. This is when I left off from honors, but as I was reviewing some stuff for this, I thought, yeah, I should write this one too, is that you can have a texture change. So like for our matchstick, it didn't just turn black, its texture changed. It became shiny and had these little vertical lines in it, so you can't have a texture change. You can have a change in the state of matter, like a solid precipitate, which the abbreviation is PPT. The match gave off light, so you have light, which is a change in energy. You can have heat, which is also a change in energy. And you can have sound, like the crackling of the match is a change in energy. See, I told you all most of this is review. So, but this is a little bit of a new thing, but we're gonna also have some review. So that was section 4.1. That was easy. Now we're on to 4.2, which is called net ionic equations. But before we learn what a net ionic equation is, we're going to just review what's an equation and what's a reaction. So we already said reactions are where bonds are broken and bonds are formed. When you have a chemical reaction, what's the original substance called? It starts with the letter R. Reactants, right? And what do you make? Products. Okay, and so atoms are rearranged, and now you have to balance them because they must obey the law of conservation of mass and energy. There's our law. Matter and energy cannot be created or destroyed. They can only change forms. Everybody remember that from honors? We are rocketing through this. This is great. Okay, next. Can I scroll on up? Everybody with me? So reactions must be balanced. We learned how to do this, and probably you learned how to do this in 8th grade honors physical science, right? So we've learned how to do this. So here's our example. Hydrogen and oxygen make water. Should I start with my hydrogen or my oxygen? Which one's easier usually? I think oxygen's easier. So I've got 1 oxygen over here and 2 over here. What do I need here? A 2. So now I have 2 times 2 is 4 hydrogens, so I need a 2 over there. Hey, everybody remember how to do that? If you hated it, it's like, uh-oh, it's still here. I was looking for a periodic table so I could show the people in YouTube land what I'm talking about. I'll grab one right here. Periodic table. Oh, where did I put you? Periodic. No, let's see. Periodic tables. There they are. Here's one. I'll grab that too. Okay. Such good TV when I wander off the screen. Okay. So there are 7 diatomic atoms, the elements that you should know. And there they are, but the great thing about it is it makes a 7. You've got hydrogen over here, and then if you start at nitrogen, see the red ones on the periodic table? It goes NOFClBri. And do you see how that makes a giant 7? So easy for learning them, making a 7 right there. Whoop, whoop. Okay, so that is, make sure you learn those. There are certain things you have to memorize in AP, and the 7 diatomics are one of them. Now, the solubility rules. This is something that sometimes I teach honors, but I don't think I really bothered last time. And did Corn teach it? Did she teach y'all solubility with double replacements? All right, good thing. Everybody can learn it. Okay, so this is something else we have to memorize. But, okay, so imagine you've got 2 ionic compounds, and they're in beakers. You've got, one is copper chloride, and another one something else like that. And right now it's just colored water or clear water. Then you pour them together. They can react and either become a solid precipitate, or they can become a gas and bubble off, or they can not react and everybody just keeps swimming around in the beaker like an ion. So what we're looking for is when they react. And so to do that, we got to know when they are soluble and when they're not. And how we do that is by the solubility rules. So I ran off for you on the colored piece of paper. Everybody look at the colored piece of paper. The solubility rules. And it's the side that has the pig on it. It looks like this. And do you see how that's a whole lot? And you're thinking, I cannot memorize all that. Never fear, there are some mnemonic devices made to memorize them. And I did not make these up. These are in every chemistry textbook and every chemistry video about this. So we remember the rules by these mnemonic devices: NAG-SAG, Castrobear, and PMS. Okay, so the first one is NAG-SAG. Now this is how you're going to remember it. I imagine a little mean pig at the barn. And old horses are called nags. And this mean little pig is making fun of the nag, calling it a nag, that's an impolite term to use for a horse, and making fun of the fact that she has saggy skin. So mean little pig is going nag-sag. So everybody's got mean little pig in your head now, right? Okay, so now this is how you remember it. Is with NAG-SAG, they are soluble. These are things that are going to stay soluble in solution. And the first thing are things that are compounds that are nitrates. So if they have NO3, they're going to dissolve. The second one is if they're acetates, C2H3O2 -1. And then group 1, the alkaline metals like lithium, these are soluble, okay? Then the SAG part is sulfates, ammonium, and group 17. Now, notice that nitrates, group 1, and ammonia all have an asterisk by them. The reason why is I got a new computer, and when I did, some of my files are gone. And one of the things that was gone was the notes I wrote last year for all of this. And last year, I feel like I went into too much depth. So I am trying to just teach y'all what's on the AP test and not all the chemistry. I'm trying to pull it back so you learn less better. That's my strategy, and so far it's working. Y'all are doing much better on the test I'm giving you than they did last year. So, meanwhile, I need to rewrite all these notes because Unit 4 is one of the things that disappeared. So I went online and I watched a bunch of other AP teachers teaching this to see how deep they went. One of the ones I watched was Jeremy Krug, and he said that the only ones that will be on the AP test, you have to know all of them for real college chemistry. But for the AP test, he said you just really have to know the nitrates, group 1, and ammonia. That's why those have little asterisks by them. Did you have a question, Kevin?
Yeah, what did my previous classes do?
What did they do for their test? So your book is a college book from Pearson, and I have the test software, so I would make the test from the test bank that the publisher provided. And I really liked it because I got to pick the questions, and they had where they told what idea it was testing you on, and if you wanted it to be easy, medium, or hard, and what format. I could make any question multiple choice, fill in the blank, write an essay. It was just like click, 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 boop, out came the test. But their tests were not any harder than y'all's. They were equal, and y'all are doing much better on your test than they did. I think it's because I'm not trying to teach them too much. I'm not trying to teach y'all too much. I'm pulling it back. And I think y'all are learning less better. Y'all are getting a better foundation, I think. Okay, so the ones with the stars are most important for AP. That is according to Jeremy Krug. Now, in addition to this, you need to remember that strong acids and bases are also completely soluble. That's what makes them strong acids and bases. By definition, they disassociate completely in water. Do you remember that from learning about acids and bases, what's strong, what's weak? Okay. So these are the exceptions. The rules are NAGSAG. The exceptions are Castro Bear and PMS. So here I've got this little bear who's supposed to look like Fidel Castro, longtime dictator of Cuba. And my son Josh saw this and he said, "Mom, this can't be Castro because he's not smoking a cigar. He's always smoking a cigar in his pictures." I'm like, no, nobody can smoke anything in public high school. So you just have to imagine real Castro would be smoking a cigar, but this is not real Castro. This is Castro Bear. Okay, so Castro Bear. So these are the exceptions to the sulfates. They are not soluble if it's calcium sulfate, strontium sulfate, and barium sulfate. So Castro comes from Ca from calcium, STRO from strontium, and BAR from barium. So I guess it's really Castro Bar, like how they pronounce it in Tennessee. Killed him a bar when he was only 3. So Castro Bar. Okay? Everybody sort of understand that? These are going to be soluble. That means the reaction would go. Now the other exception is PMS, and I drew a sad face because PMS is sad. You feel sad. So the PMS here is P is from lead, the symbol for lead. M is from mercury, the word mercury, not the symbol. And S is for silver, the word silver, not the symbol. I didn't make these up. These are in every college textbook, but that's what it is. So these are the exceptions to halogens and sulfates. If they're bonded to these, they're going to precipitate out. The reaction will not just all hang out as ions, it'll do that. Now there's another exception, that's CCP, and that's why there's a hammer and sickle. The CCP is the Chinese Communist Party, right? So we're going to remember these things. Castro Bear, he's communist too. We have a lot of communism today in our news. Okay, so and it is that chromates, carbonates, and phosphates are also an exception, but according to Jeremy Krug, you don't have to learn them for the AP. So not important. Okay, so this is our new thing. I put stars on things that were new for this chapter that you didn't learn in honors. And the first one is net ionic equations. When compounds dissolve in a solution, you're used to writing them as complete molecules, ionic things, or covalent. But in AP and in college, we don't write them as compounds anymore. We go ahead and write them as ions in the equation. And if it's an ionic equation, you show everything and you show the ions. If it's a net ionic equation, you only show the particles that change in a reaction. You cancel out the things that don't. They're called spectator ions. They're just floating around watching what's happening. They're not doing anything important. We mark them out. Now, I think this is kind of fun. I enjoy canceling things out in math when I have it in the numerator and denominator. I enjoy this too, marking out chemicals. There's just something nice about getting rid of the unimportant ones and just writing down what's important. So a spectator ion is not involved in the reaction, and it will stay the same phase throughout, usually an ion floating around in a beaker of water. Okay. Now, how you do this? First, you write the balanced regular molecular equation. Then you rewrite it where anything's an ion, you divide them up into ions. They will try to swap in a double replacement reaction. Remember that one where the cations and the anions swap? So then you remove and cancel out the spectator ions, the things that aren't doing anything, by looking at the solubility rules. If they're all spectator ions, then you write no reaction. If nothing dissolves out, you just write no reaction. Now, according to Jeremy Krug, he says they're not giving you no reaction on the AP Chem test. Or if they do, they'd only give you like one. You're not getting a lot of no reactions. I like no reaction. I like writing NR, not having to do anything else. Ensure the net ionic equation is balanced by mass and charge. So this is a little different. We're used to balancing the atoms. We're going to also balance charges in this. So here's an example. Here's a molecular equation. Silver nitrate plus sodium chloride makes silver chloride and sodium nitrate. So, but see these that say aqueous? They're ions. See the one that says solid? That one's not. So we write the one that did something. It stayed together as a solid. We write it down as a solid. Everything else we break up into its ions. Silver nitrate, sodium chloride, sodium nitrate. Now we look and say, what do I have the same thing on both sides of the arrow? Well, I have a sodium here and a sodium there, so I get to mark them out. Okay. I have a nitrate here and a nitrate there, so I get to mark them out. And then you just write down what's left, what you didn't mark out. Now, why did silver chloride become a solid when halogens are supposed to be soluble? It was the PMS exception, S for silver. So that's how it works. How do we feel about this new information? I think once you practice it, it's pretty easy. We'll practice it and I'll show you more. All right, so here's another example. Here I have lead nitrate, potassium phosphate, lead phosphate, potassium nitrate. So I look to see what's actually doing something that it's going to be written as that. Everything else breaks into ions. So this is the tricky part, everybody watch. When this breaks up, this 3PbNO3 taken twice, it's going to break into one lead ion, but it's going to break into two nitrate ions. Do you see that? And we have a 3 in front of it balanced, so I'm going to have 3 lead ions. I'm going to have 3 times 2 is 6 nitrates. Everybody see where I got that nitrate from? It's because, think of these are little groups of balls that are breaking up, and we're going to have 6 of them. So now we have this, and we can mark out everything that's on both sides. So the PB's not, the nitrates goes there and there, those mark out. The potassium here marks out with that one there. That one, it doesn't mark out, that one doesn't mark out. I write down everything that's left, and so this I have 3 leads here, see it's 3, and for this one I have 2. Now, before I'm done, I gotta make sure the charge balances. So here I have plus 2 times 3 is plus 6, and here I have 2 times negative 3 is -6. And over here I have a neutral solid is 0. Is this true? Is 6 minus 6 0? Yes. So we are good to go. Okay, how do we feel about that? Can we do it? We're going to do some more. We'll practice. Okay, so here is another little thing to think about. So there are 3 compounds, carbonic acid, sulfurous acid, and ammonium hydroxide. They all react, but instead of making a solid, they make a gas. So it just can't all stay swimming around in the beaker. Mostly it's going to become a solid precipitate, that's 99% of the time. But every now and then you get one of these that make a gas and fly off. That's also a reaction, it's actually doing something. So just know that. Okay, now we're back to stuff you learned in honors. Synthesis reaction. Here zinc wants to replace hydrogen to make zinc chloride and hydrogen gas. Do y'all remember learning about the single replacement reaction? I said it was the affair. Zinc is trying to cut in and take chloride away. Hydrogen and chloride are in this very happy relationship. Mean old zinc is trying to cut in. Okay, that's what's going on. Can it happen? Because you know there's true love that's a fair proof. Is hydrochloric acid a fair proof, or can zinc cut in? Well, how we know is the activity series. Everybody look at your colored piece of paper, the other side. The super cat side, not the pig side. And this is an activity series that lets you know if things can replace or not. If the elements on top can replace the ones that are lower. So for example, the stronger is on top, the weaker is on bottom. And then notice for what's written down at the bottom of the page. Okay, look right there on your page. It says metals from lithium to sodium. Let's find sodium here. It's in the middle here somewhere. To sodium will replace hydrogen in acid and water. Ones below sodium will only replace hydrogen in acid. So now look up here. This metal is trying to replace hydrogen. Is HCl an acid? Yes, that's hydrochloric acid. So is zinc going to be able to cut in? Yes. Yes, it will replace. Will this happen? Yes, and it's because of that rule. Okay. So what about our other metals? Can gold replace copper in this chart? No. Gold's a wimp. Gold can never replace anybody. That's why he's uncombined in nature. Look at him. He's at the bottom. He can't replace anybody. Okay, how about can aluminum? Look at the chart. Can aluminum? Yes. Joseph said yes, and he's right. All right, everybody understand how I use that chart? It's from honors, but you need a review. Okay, next idea is oxides. So this is something you just need to kind of remember, but I think it's easy, is metal oxides will undergo synthesis reactions with water to produce bases. And we saw this in lab. We put calcium in water and then added phenolphthalein, remember that? And it was blue. But you can remember this just from the name. Group 1, Group 2, alkaline metals. Alkaline is an old-fashioned word that means base. Alkaline earth metals. So these metal oxides will make bases. Non-metal oxides undergo synthesis with water to produce acids. Okay. So synthesis is one type of reaction. Atoms get together into something new. Compounds are made in synthesis. So this is falling in love. Aww. Decomposition. If you can fall in love, you can break up. So let's draw a broken heart. Poor breakup. So decomposition, compounds are broken down. And decomposition so like bodies break down in the grave. So we have a little rest in peace. And they are decomposing, right? So here we have one chemical that broke into 3. That's decomposition. Y'all remember that from honors? Those reaction types. Okay, neutralization. We learned this in honors too. What happens if you combine a strong acid and a strong base? You get salt and water, right? That's why we got little dude here on the beach. He is salt and water. Ta-da. Okay, here is the reaction written down for this. Hydrochloric acid, an acid plus sodium hydroxide, a base, makes water and salt. Now, what if you combine them? These are strong. What if you combine weak ones? They don't disassociate completely or react completely. So, just the opposite. Now, section 4.3. Look how fast we're going through this. This is something you already know. AP Chem likes to make you draw and interpret pictures of atoms and molecules. So here's an example. We have some oxygen and some hydrogen, and then we have something happen. What's happening in this picture? What are we making? What's made out of hydrogen and oxygen? Looks like Mickey Mouse. Water. We're making water. Notice when you draw something like this, you don't just draw the water, you have to draw the things that didn't react too. So make sure you count the molecules and you know, they're looking for numbers in these boxes. And they will ask you questions based on that. Sometimes you have to pick the picture like you have on your test. Sometimes in the free response you have to draw the picture. All right, that's okay, isn't it? Not too bad, drawing little pictures. The next thing, physical and chemical changes in more detail. So this is something that's a little bit harder to think about. So we know that if you take water and it does phase change, it is a physical change, not chemical. But what if you dissolve salt in water? Do you think that's chemical or physical? It's chemical. Because a chemical is whenever bonds are broken and formed. Ionic bonds are broken, aren't they? So that's like a question they've asked in the past that's a little bit tricky. You'll be ready for it if they bring it back, okay? Stoichiometry, do we remember this from honors? Good, okay? So stoichiometry, how much does a reaction make? How much stuff do you need? Stoichiometry is mass and quantity relationships among reactants and products in a chemical equation. It's what the coefficients or number of moles, there's our little mole, what they tell you. It's not that kind of mole. Okay, how you do these problems. The first one, you balance the chemical equation, and that's going to make a table where we can keep up with all of our information. Then you write what you don't know and don't know, your unknown, under the chemicals. And sometimes you have to first use conversion factors if you need to make the units consistent. Next, you will write the next line. It'll determine what the next line is determined by what you have for your knowns and unknowns. If you have known or unknown in grams, what do you have to have? What goes with delicious graham crackers? M&Ms. So you need molar mass. So what I always tell my kids is imagine a delicious graham cracker. I'm putting peanut butter on mine. If you're allergic, don't imagine you're putting peanut butter on yours. And then put some M&Ms to make them stick, and then take a bite so you can remember whenever it has grams, you need molar mass. Yes, Kevin? Go ahead. All right. So what about if that line has liters of gas? What goes on the next line? Do y'all remember that? It's a number. Yes, Joseph knew it. 22.4 liters per mole. What goes on the next line if you have atoms, molecules, particles, something like that? Avogadro's number. Does anybody remember what it is? 6.02 times 10 to the 23rd. What about if it has moles? That's right, you put nothing. Everybody did a good job saying nothing. That was awesome. Okay, so that's our second line. Our third line is you write the mole ratio, which are the coefficients from the balanced equation. Then you draw a U. Why do you draw a U? To tell you what you do, the order of what you do, and that's where a lot of kids get wrong. They'll mix up and start at the wrong place. So the U tells you what to do next. Then you set up your train tracks and you do the math. And when you draw the U, it looks like it's smiling at you, so I drew a smiley face. It makes the problems nicer. So here is an example. Making banana flavoring. Okay. How much, you have 45,000 grams of isoamyl alcohol. and enough acetic acid, that means that's not important, to react with it. How much banana flavoring can you make? This is a grams to gram problem. So we write down we check to see if our equation is balanced. It is, so I'm going to give it a little check. I write down what I know and don't know. 45,000 grams under the isoamyl alcohol. What I don't know is the banana flavoring. I do question mark grams. I have grams, so what goes in the next line? M&M's, molar mass. Where do I get the molar mass? The periodic table, right? And did y'all notice on the Emily Miller things, she does this curly U for molar mass? So don't let that confuse you. All right, so I would look up carbon is 12 times 5, plus hydrogen is 1 times 12, plus oxygen is 16, add them up and get 88. And then I have to do the other side, 12 times 7 plus 1 times 14 plus 1 times 16 plus 2 is 130. My next line is the coefficients from the balanced equation. That's a 1 and a 1. Now I draw my smile. I start from what I know and I draw an arrow to what I don't know, so I remember to go in this order, because sometimes it goes the other way, and that's when kids miss it if they don't draw their smile. Now I'm ready to draw the conversion factors. I want you to draw what the textbooks call train tracks, not parentheses, because I've done this for a long time, and I've seen kids turn their parentheses into sixes and then get their question wrong. Nobody turns train tracks into anything. So do the train tracks, not the parentheses. So we start with what we know always. We take the units of what we know and we push them to the denominator. So we had grams of isoamyl alcohol. We write grams of isoamyl alcohol in the denominator. We go around our circle to look to see what number goes with grams, and it's 88. What goes on the other side of the fraction bar? That per is a fraction bar, so moles go on the other side. What number goes with that mole? 1. That's 88 grams per 1 mole isoamyl alcohol. I take my units and push them to the denominator. Now, I like to do sound effects with this. It makes it more fun. So moles of isoamyl alcohol go to the denominator. I go around my U to see what number goes with them. It's a 1. What goes on the other side of the fraction bar? A 1. A colon in math is a fraction bar. You learned that when you learned about ratios. You could write them as a half or 1.2. Remember that in math? Okay, so now we're here. Now we're to the banana flavoring side. We push the moles of banana flavoring to that's not boron and fluorine. This is banana flavoring. I didn't want to write it all. You probably should. I was being lazy. Okay, so I push moles of banana flavoring to the denominator. What number goes with moles of banana flavoring? Well, it's that mole right there, and it's a 1, because that's grams per 1 mole. You just don't write it. And what goes on the other side of the fraction bar? 130 grams of banana flavoring. I mark out the things that are the same in the numerator and denominator. I multiply every number on top. I divide the numbers on bottom. You can ignore 1, because anything multiplied or divided by 1 is itself. I'm going lightning fast, but y'all already know this, right? And you'll stop me if you don't. So 45,000 times 130, enter, divide by 88, enter. Somebody do it on your calculator and tell me what the answer is. See if y'all get it. Tell me the whole number on your calculator. Don't, like to the ones place. I think Jacob's doing it for me. What'd you get?
I got 66,477.2727.
Okay, so is this the answer we're going to find on the AP Chem test? No, why not? Sig figs, right? We have 45 zeros, no decimals, so how many sig figs should we have? 2, so what should we say? 66,000 no decimal point grams. Okay, everybody remember that from honors? Easy. Okay, let's go on. The next kind of problem, and these will be on the AP test. So just know you're going to have a couple of these. Take the time and do them. If you're doing all the fast problems that you're supposed to be doing fast, you'll have time to do them. So don't feel antsy in the pantsy and skip them. Do them. Y'all know how to do them? Do them. Okay, example. Okay, so this is my brownies. So limiting reactants. This is what I always say to think about with brownies. Some people use sandwiches. There's even a FET lab with sandwiches. Some people use candy. We're going to think brownies. So I'm going to a party, and I signed up to bring brownies. I went to my favorite grocery store, Food Depot, because they're cheap, and I buy my favorite kind of brownies, Ghirardelli. I get 4 boxes. I go home. I have a big jar of oil. That's good. I've paid my water bill. All the water I need is in the sink. But eggs, I've only got 2. Am I making 4 batches of brownies? No. If the recipe calls for 2, I'm making 1 batch. If the recipe calls for 1 egg each, I'm making 2. And that's it, right? Unless I go back to the store, eggs are my limiting reactant. Okay? So think about brownies and then do it twice. So what do these problems look like? They have 2 givens. So you had 152 grams of carbon monoxide and 24.5 grams of hydrogen to make methanol. What is your limiting reactant? How much methanol can you get? So you write down your grams. What goes with grams? M&Ms. So we do the molar mass next. 12 plus 16. 1 plus 1 is 2. 12 plus 4 plus 16 is 32. Then I look at my balanced chemical equation for the next line. It's 1 to 2 to 1. Okay, everybody good so far? Next, I draw my U, and I do one at a time. I'm going to do carbon monoxide first, and I like to make this have 2 different colors. So I'm going to draw my first U in blue, and I'm going to pretend like the middle part's not there. Okay, so I just go around 152 grams, push it down, 28 grams, 1 mole, push it down. I pretend like that 2's not there because it's part of the middle part. Then 1 mole and 1 mole going around 1 mole 32. Somebody do on the calculator and see what it is. 152.5 times 32, enter, divide by 28. What'd you get? Somebody tell me what it is. Yes, sir? 74.2, is that what you said?
0.28, so
that'll do good enough. Okay, so that's our first one. Now we do it again with hydrogen. Let's pick a new color. We'll pick, let's pick orange. I like orange. Okay, so now I put my dotted hydrogen and I go around with my second U. So this time what I know is, I put 24, is 24. I wrote it wrong there. I should correct that on my thing. Right here. 24.5. So I need to correct. Is y'all's wrong too? Okay, y'all correct that. Okay, 24.5. Okay, so 24.5. And then what goes in the denominator here is 2 grams. Other side of the fraction bar, 1 mole. Push it to the denominator. This time it's 2. Everybody see that? Don't forget that 2 goes in the denominator. 1 mole in the numerator. 1 mole in the denominator. 32 grams in the numerator. Grams cancel out. Moles cancel out. Moles cancel out. I'm left with grams. Somebody put it in their calculator. 24.5 times 32, divide by 2, enter, divide by 2, enter. You have to hit enter twice or use parentheses. Yes, sir?
196.
That sounds right to me. 196. Now we ask ourselves, self, which is less? That's why we have Pac-Man here. He's being our greater than, less than symbol. Which is less, 174 or 196? 174. So this is what will really happen. So carbon dioxide is what limits. Our hydrogen is in excess, is our vocabulary for that. Okay, everybody remember that? Okay, so next is what always comes next is percent yield. So this makes a very good multi-part free response for the AP test. Do you see that? Then you can just go one to the next. First you have to balance the equation. Then you gotta You know, but I'll tell you something else they'll probably do. Okay, so what if you only got 150 grams? What's your percent yield? Actual over theoretical times 100. And so what is that in our calculator? Somebody put that in and tell us our percent yield. What's 150 divided by 174 times 100? How much? Y'all need to have your calculators out, calculating along. What'd you get? 86.2. So then what the AP test is going to ask you next is, why do you think you only got 86%? And you have to say, I left some in my beaker, or I spilled some on the floor, or this is a weak acid, so it doesn't disassociate completely. So therefore it didn't all react. Do you see what they're going to do here? Okay, so then the other thing they'll do to make this tricky is, so instead of just giving you grams or liters or particles, sometimes they'll give you a liquid, volume, and concentration. And first, before you do the problem, you have to use molarity equals moles over liter to get the moles first. And sometimes they'll give you a density and a volume, and you have to solve for mass before you get started. Do you see how tricky how they can put a little trick in there? They can make you do a little something before you even get started. That is a beautiful AP multi-part question ready to go. So I put a little rabbit because it's tricky. He's being the tricky rabbit. Okay, titrations. Titration, in every one of these units, you notice we are getting a lab technique. We did chromatography. We used spectronomy. Now we're going to learn about titration. Now, I've heard that Korn's class has done a titration. I did not do it with honors this time. But don't worry, we will. We're going to do it. So this is our lab technique this time. It's an analytical technique. We did use burettes when we did metric Olympics. We just didn't use them for titration. So what you do is you have that tall, skinny thing. Usually you put a base in here that is a known concentration, a known amount. You read what it is to start with. You have what you're going to react to in the bottom, usually an acid, and you add some indicator like a phenolphthalein. You add base till it turns pink, and that's when it is the limiting reactant has reached its limit, and your moles are equivalent. So you swirl it. You don't want to overshoot it where it gets real pink. You swirl it and get it barely pink, and we will do that lab. Okay. So this is it's used for acid-base reactions, something called redox reactions, and precipitate reactions. For acid-base, the equivalent point is when moles of acid equal moles of base. Now, what do we mean by equivalent point? So equivalent point is when it's done, when you've reached what's called the end point. So what you write down is you start off with the molarity of your known, which is in the burette, the initial volume and the final volume in the burette, and then you're going to either have the volume or the mass of what goes in the Erlenmeyer flask. The fastest way to do this is to do the math so you kind of know what the answer is going to be before you do it. Otherwise, you sit here going drop, drop, drop for hours trying to find this equivalence point. So we want to do the math so we can get there quickly, and then stop before there and then go drop, drop, drop. Then you graph them, and the graph, the equivalence point is the middle of this vertical line. That's what you're looking for graphically. Okay? We'll do it and it'll make more sense. We'll do a lab with this. Okay, this is your new idea for AP, redox reactions. Ella, are you with us? So everybody needs to pay attention hard right now because this is a new thing. I know that all that was kind of review, but now it's time for something new. Now we touched on it in honors, redox reactions. In this reaction, electrons are transferred. Now, remember how I told you chemistry is older than chemistry? Well, this is one of them. If y'all remember that video we watched, The Mystery of Matter, and we learned about Joseph Priestley and Antoine Lavoisier and how they were studying calx, and it had to do with oxygen. They found out calx didn't exist. Remember all of that? So these reactions, what makes them what they are is electrons are being transferred. They thought it was oxygen being transferred. So they named things that we still call it that are a little confusing. But don't worry, Leo will help you. So just like how I didn't make up NAGSAG, I didn't make up Leo. So what you're going to remember is Leo the lion says grr. So here's Leo, and he is ready to help you. And this is what it is. So electrons are transferred, not oxygen. Leo the lion says grr. So this is the confusing part. When electrons are lost, it's called oxidation. Okay, that's not the hard part. It's the next part. When electrons are gained, it's called reduction. Okay, that's the hard part. But don't worry, just remember Leo and you will be okay. Okay, so the gain of electrons is called reduction. When electrons are lost in oxidation, the charge goes up. When it is reduced, the charge goes down. So here is our example problem. Here we have zinc wanting to replace copper in this reaction. Zinc wants to be with the sulfate and copper go off as a solid. Okay? Y'all see what's going on? Okay. So if we look at the zinc had 0 charge and now it's an ion. Is it an anion or a cation? Is zinc going to be an anion or a cation? It's in the front, so what is it? Did it gain electrons or lose them? Think about sodium. Sodium's a metal too. Does sodium want to gain electrons or lose electrons? It wants to lose, because remember, it wants to be like neon. So this zinc is going to lose electrons. It's going to become positive. So zinc loses electrons. It increases its oxidation state. It went from 0 to positive, so it is said to be oxidized. Okay? You can get it if you think about Leo. Okay, so we're going to do labeling a lot of stuff with this. What is being oxidized and what is being reduced? Okay, in our problem, the copper was the opposite. Copper gained electrons and decreased their oxidation state. Copper was reduced. So let's go back and look at that so we can see it happening. So copper was an ion. It was positive. And then it became 0. So it lost electrons. Do you see that? It went from a positive to 0. Can you see that? It had, so it gained electrons. I think I said that backwards. Okay, so copper gains electrons and decreases its oxidation state. Copper is reduced. Now this chemistry is, salts are important for it because salts dissolve in solution. We're going to learn about how liquid batteries have something called a salt bridge. We're going to come back to this all later. This has to do with how batteries work and things like that. So when you do this, you notice the only thing really having something happen were the metals. We don't write the sulfate, it's spectator. So zinc went from solid zinc to +2 in aqueous. Copper went from aqueous to solid. Can everybody sort of see what happened? All right, so now here's another new concept. We're going to go back to that at the end of the notes. Here's another new concept for AP. Remember when we learned oxidation states, 1, 2, 3, skip, -3, -2, -1, zip? You know that whole skip thing and the whole thing about how we just don't worry about those transition metals? Well, today's the day we're going to start worrying about the skip and the transition metals. Okay? There's more to it than 1, 2, 3, skip. Okay? And this will make more sense once we do some problems. Remember when we learned significant figures? It was a long list of rules that sounded like gobbledygook till you tried it and then it made sense. This was the same thing. we've got a list of rules that we use to figure out the charges, and it's going to sound a little bit like gobbledygook till we try it, okay? But just try to listen and see if it makes sense to you. Okay, so here are the rules. If something is by itself, its oxidation state is 0. So it could be oxygen all by itself, sodium. If it's just one element, all pure, it's 0. Rule 1. Rule 2 is ions have the charge they are labeled with if they are labeled. So if they give us a charge, that's the charge. We don't second guess it. Whatever they give us, then that's a given, we go with it. Rule number 3, in a compound, the sum of all oxidation states equals the overall charge. So if it's a neutral atom, if it's a neutral molecule, it's all going to add up to 0. If it's like a polyatomic ion, it's going to add up to its charge. Does that make sense to you? It'll make more sense when you go. But just know the compounds have to be added up. Fluorine is always -1 because it's most electronegative, it's not going to change. Oxygen is usually -2. Now, so you can remember oxygen is -2 because according to Jeremy Krug, I watched his video, he said they're not going to give you the exception of peroxides on the AP test. You'll have it in college, but other than that, you won't have it on the AP test. But there are some exceptions for oxygen, only when it's in like H2O2. Hydrogen is usually +1 when it's bonded to a non-metal. It's the opposite when it's bonded to a metal. But right now, hydrogen usually has an oxidation state of +1. In a binary, that means something made out of 2. The more electronegative element is assigned a negative oxidation state. This means the less electronegative element is positive. I promise it'll make sense. For monatomic ions, the oxidation state is equal to the ion's charge. For example, sodium is +1. That's just saying, otherwise, if you don't know, you go with one, and you go with 1, 2, 3, skip. When in doubt, if there's no other clue, you go with 1, 2, 3, skip. Okay, all right, let's do it. Y'all are gonna understand it, I promise. Okay, where did we get to? We did all that. We're already on that page. We're here. Okay, so the thing, carbon is in skip column, right? So today we're not going to skip. Oxygen is what we know. According to 1, 2, 3, skip, what is the charge of oxygen? -2, okay? And we have 2 of them. So it is -2, and we have 2 of them. What is -2 times 2? -4. The whole thing has to be neutral because that's a neutral thing. What -4 equals 0? So what's x equal to? +4, right? So the way to get 0 is 4 minus 4 is 0. That's how you do it. That's not so terrible, is it? Let's do some more. Let's get you good at it. If you have ones that don't follow these rules, the more electronegative atom with the 1, 2, 3 rules and solve for the other one. It'll make more sense in a second. Let's do another one. Okay, so P and chlorine. Of these two, chlorine is the one that had the rule about that halogens are usually your -1. So I have 5 of them. What is 5 times -1? 5 times -1, this is not hard math. -5, right? So my chlorine is -5. The whole thing is neutral, so what does P have to be? P has got to be +5. Now, is P normally +5? No. But these are, you know, this is our new thing. This is when it's not the normal thing. Does everybody understand how I got +5 for that? Okay, let's try this one. So this one, we have oxygen. Oxygen has the rule in the list. It's -2. I have 3 of them. So 3 times -2 equals -6. Nitrogen is what I'm not so sure about, but all together, it's got to equal -1. So what is nitrogen going to be to make that -1? Maxwell's doing it. It's going to be a 5. -6 plus 5 is -1, right? This isn't terrible, is it? Okay, so here's another one. This one's a little more complicated. We're going to start with our oxygens. We have 7 of them, and they're -2 each, so that's -14, right? Chromium is there in the transition. That's the one we don't know. We're going to have to figure out. Sodium, we don't have anything else going on, so we can go with 1, 2, 3, skip. Sodium is +1, right? And I have 2 of them. So 2 times 1 is 2. Chromium is what I don't know about, but I do know that I have 2 of them. So I need to make that, and overall it needs to be equal to 0. You need me to explain that one more time? I see some confused looks. Okay, I started with oxygen. Oxygen's -2. I have 7 of them. -2 times 7 is -14. Sodium, I know it's a 1 because it's in that first column, and I have 2 of them. 1 times 2 is 2. Chromium's the one I don't know. It's the transition metal. But I do know that I have 2 of them, but it's unknown. It's X, and if I solve for X, I'll know what it is. So +14 over here, -2 is 12 divided by 2. X equals 6 or -6? I just did it in my head. X equals +6. Nope. Okay, now let's try it. Sometimes they'll make you do a whole reaction. Okay, so let's do it. Hydrogen is +1, and I have 4 of them, so what's carbon going to be? What plus 4 equals 0? I got to be going too fast because you are starting to not answer. Maxwell knows that carbon has to be 4. Is it +4 or -4? -4. Maxwell's answering back there. All right, so that works now. Carbon has to be -4 because hydrogen is +1. Y'all good with that? So that carbon was our weird one because it was in the skip category. Now oxygen is normally 2, but oxygen's all by itself. So what is oxygen? 0. So oxygen is 0. We'll draw little lines to separate these. Okay, oxygen here is -2, and I have 2 of them. What do I add to -4 to get 0? +4. So our oxygen here, these are equal to -2. Our carbon equals +4. Now notice, here carbon is -4, here it's +4. Okay, there's a reason why we waited to teach you this. Okay, let's look at water. Oxygen is -2, and I have 1 of them. So what does hydrogen have to be?
2.
It's got to be 2. Hydrogen, they're 1 each though, so they're +1. All right, so now we have them all labeled. Now this is the next part of the AP question. Who is being oxidized and who is being reduced? So carbon is going from -4 to +4. Did it gain or lose electrons to go from -4 to +4? Electrons are negative. It had some and now it doesn't, so it lost them, right? So our carbon over here went from -4 to +4. It lost electrons, so it is oxidized. Leo. See, I told you Leo's going to help you. Okay, now let's look at hydrogen. Hydrogen was +1, it's +1, it didn't have anything happen. So let's look at oxygen. Oxygen was 0, and it went to -2. It went from 0 to -2. Did it gain or lose electrons? Electrons are negative. It gained them. It didn't have any, and now it's got 2, right? So it gained electrons. The gain of electrons is reduction. It was reduced. And that is how you do these problems. That's your new concept. We'll practice it, you'll get good at it, I promise. Okay, back to something you already know, acids and bases. pH tells you how acidic or basic. This is going to be later. This is not on this test, but y'all already know it. Acids taste sour, they start with H. They have hydrogen ions by Arrhenius, or they donate a proton. The proton is a hydrogen ion, according to Bronsted-Lowry. Or it has the hydronium ion by Bronsted-Lowry. So there's hydronium. They react with metal, they turn blue litmus red, their pH is lower than 7, and an example is lemon juice. Bases. See, all that was a review, wasn't it? Taste bitter like soap, they often end in OH, that's Arrhenius. Or they accept a proton. Bronsted-Lowry, we talked about the reason why, is ammonia. We've known about ammonia since ancient times. Amun-Ra, the god of Egypt, is what was named after. Remember, nitrogen has got that little unshared pair, and it's a base. So a proton comes and snuggles up to that unshared pair, and then so that's why it's basic. It feels slippery. It reacts with fat. It turns red litmus blue, and its pH is greater than 7. There's our OH. It's an example of soaps. So all that is a review. Strengths. Strong acids dissociate completely in water. They're very dangerous. They have a low pH. And the examples of strong acids you're going to have to memorize, but not for this test. We're going to come back to acids and bases in a later unit, and you'll need to memorize them, but you can go ahead and start memorizing them. The examples are sulfuric acid and hydrochloric. Wheat are things a lot that we eat, like vinegar. Acetic acid is the acid in vinegar. Citric acid, lactic acid. Also, you're going to need to know for the other one, the organic acids are weak and they have Cu in them, but that's not on this test. They do not dissociate completely. Strong bases. They're very dangerous. They have a high pH. Example is sodium hydroxide. Lye is the common name of sodium hydroxide. How can you tell? With an indicator like litmus paper, universal indicator. Sometimes you're, okay, so that is all review of honors, right? We all know that. So now what about this? Sometimes they will ask you to make it a little harder. For AP, they'll ask you about mole ratios. So here we have a base disassociating completely into calcium and hydroxide. Sometimes they'll want you to look at the balance coefficient, 1, 1, 2. You see that? And they'll say, if this is 0.7 molar, then what are the molarities of these? Well, this is 1 to 1, so that mole ratio, that is also 7 molar. But this one's 2, so it's times 2, 1.4. So that's a very AP little thing to do with that, to look at those mole ratios. Okay, conjugate acid-base pairs. But I teach this to honors sometimes. I did not this year. Did Ms. Korn? Do y'all know conjugate acids and bases? Okay, so what it is that for every acid, it has a conjugate base. Acids and bases go together. So how do you find, and what you have to do on the AP test is you have to label them. So this is sort of just a identification thing. And how you find them is they look alike except for an H. So here we have this acid, it's an organic acid, it's going Cu, and it loses its H. Do you see that? They look alike except for the H. Everybody see that? So they're a pair. I'm going to draw a little whoop whoop in between them there. Okay, and then these two look alike except for an H. Do you see that? So they're a pair. I'm going to change my color, make it prettier. So they're a pair. Now, which one's the acid and which one's the base? Well, I kind of gave it away. I told you that one is the acid because it's the one that lost the electron. So this one, let's go back to red here. This is the acid, and this is the one that looks like it without the acid. It's the conjugate base. And now let's do these. The H3O, that's the hydronium ion, it is acid by definition, right? We know that's an acid. So this is an acid. So that means water here is acting like a base. Water can act like an acid or a base. Isn't that weird? So this is the base, and then that is called its conjugate acid. Think he can do these? So there'll be an acid and base on one side, acid and base on the other. You figure out what one is, and you can usually figure out all the rest. So here's another one. Here we have ammonia. And what it looks like, ammonia we know is a base, right? So what is this one over here? This is its conjugate acid. Okay, now we've got these two. Ammonium, he gained an electron. I think I wrote that backwards. Hold on. No, I didn't. So that's the conjugate acid. That's water. Okay, so let me go to a different color. Okay, so OH is a base, right? So this is the conjugate base. I'll make this line red. And so that means here water is acting like an acid. Acid and base, acid and base. Okay, so water can be both, so it's called amphoteric, because it can be either one. Now, here is back to our new idea, redox reactions. Our two new ideas are redox reactions and oxidation states. Okay, so metals with metal ions, you ought to remember that metals tend to be oxidized. Okay, that's just handy to know. So here is a redox reaction, and we're going to look at it, and we're going to figure out what are the spectator ions, and we're going to learn how to balance them. And how you balance redox reactions is a little different than regular things, because you have to balance the charge and the number of atoms, and how you do it is called the half reaction method. I'll show you. Okay, so here's our thing. We got barium ions reacting with silver nitrate. It's aqueous, so that's really broken up, making silver solid and barium nitrate ions, so that's really broken up. So first, we write down what is going on with the ions, but remember I said it's really just the metals that matter and not what they're bound to when it is this metal trying to replace another metal. So we can just not write those down. Okay, so now we look at this and we're going to separate what's going on with the barium and what's going on with the silver. So first we write down the barium. Barium is becoming a barium +2. And then our silver is going from silver to silver solid. Silver ion to silver solid. Then we look at it and the charge has to be the same. Here barium is neutral, there it's +2. So I have to add 2 electrons because +2 minus 2 electrons is 0. I got to make it neutral. So here I'm adding electrons at the product there, and my electrons went down. I went from neutral to +2. My electrons have gone down. So I need to add 2 to balance it out. Now look at this one. I went from +1 to neutral. I need to add an electron so that -1 + 1 is 0, because my electrons had gone up here. Then once you do this, you have to add them up where you cancel out the electrons on both sides. So I only have 2 electrons here and only 1 there. So I'm going to multiply this whole thing by 2. So this is going to become 2 electrons, a 2 here, and a 2 there. Now I can add them up. The electrons cancel out, and I just write everything down. The barium, the 2 silver ions, the barium ion, and the 2 solid silvers. And once again, I promise This gets easier the more you do it. It's a little like, remember in algebra where you did combination on the system of linear equations? And you'd have to multiply the whole equation by something and then add it together so that one of your variables cancel out? Same thing, but this time we're just doing electrons instead. Okay, so sometimes these don't work and you have to check the activity series. These can be no reaction, but according to Jeremy Krug, they're not going to give you no reaction on the AP test. Okay, and he also said that you should memorize this half reaction, this net ionic equation actually for water being reduced. He says that is just handy. They will often ask it to you, and so that you don't have to sit there and figure it out, you can just write it down in your free response real fast. Okay, so there's an activity series for halogens, just like how there is for the metals. It's right here. So this is halogens try to replace each other, and there's a strength chart. But the good thing is you don't have to look at it or memorize it. It is the order of the periodic table: fluorine, chlorine, bromine, iodine. So like bromine can replace iodine, iodine cannot replace bromine. Okay, all good there? So here is another little problem with the halogens. I already said it. Here is bromine wanting to replace iodine, and it can. Bromine can replace iodine because it's on top. Okay, this is a little concept we're going to go over real fast because according to Jeremy Krug, it's not on the AP test, but it would be nice to know about. There's something called a disproportionation reaction, and this is where the same element can simultaneously be oxidized and reduced. Y'all saw it in my classroom. Do you remember when we did the lab where we put little drops on metals? Do you remember that? And one of the ones you did is you put copper nitrate on copper metal, and it appeared to react. And every time people go, why? Why would copper replace copper? This makes no sense. Okay, it's this. So if you had a beaker of iron, some iron, iron chloride, iron nitrate, something like that, and it sits for long enough, then some of the solution, so we've got our iron ions floating around, some will settle out and get together and make iron solid. And some of it will turn from iron 2 to iron 3. So some of it's gaining electrons and some are losing. So just know it's out there. And I sort of wanted to touch it because my kids always ask about it. And I'm like, it can do it. Sometimes I'll explain it to them when they'll ask. I'm like, remember, there's more than one copper. There's cupric and cuprous, right? So some iron becomes solid, iron is reduced, some becomes iron ion plus 3 and is oxidized. Okay, now what about metals reacting with strong metals? So here we have magnesium reacting with hydrogen ions, protons to make magnesium ion and hydrogen gas. So this time it's gas produced instead of a solid. Now, more about balancing redox reactions with acids. Some are a little bit tricky. So here we've got chrome with our half reaction. We'll have chrome with oxygen going to just chrome. Where did the oxygen go? Any ideas? It's not in our reaction, so it didn't react. What happened to it? The thing is it's an acid. So it goes into the solution with the acid. So here's the example problem. Write a balanced net ionic redox reaction of iron 2 ions in an acidic solution with dichromate ions, producing iron 3 ions and chromium 3 ions. So first you write the balanced half reaction. Iron 2 becoming iron 3, and this ion they said is going to become this ion, okay? So the first thing we need to do is make sure that our numbers here are balanced. And do you see how I have 2 chromes over here and 1 chrome over there? I need a 2. So that's step 1. And we can also look and see what's what is reduced and what is oxidized. Okay, so first balance the atoms other than O and H. So this one's already balanced, I balanced that one. Next, balance the oxygen by adding waters. So I have 7 oxygens over here. So I'm going to put 7 waters over here. Because it's in an aqueous solution, I can do that. We got waters we can play with. Okay, then it says balance the hydrogens by adding H's. Well, I've got 7 times 2 is 14 H's over here. I can add 14 H's over here because this is an acid. And what does acid have? H's floating around, right? So I can add hydrogen ions right there. Okay, so now we're doing all right. Now we're going to balance the charges by adding electrons. So over here I've got +3, and here I have -2. So I need to add 1 electron over here so those balance out. Do you see that? Here I've got 2 times 3, which is 6 positives. I need 6 negatives over here. So I add 6 electrons over there. Now I need my electrons to cancel out. So I'm going to multiply this whole thing by 6. And this will be 6, 6, and 6 electrons. It's not evil, I promise. Okay, so I'm just multiplying all that out. Now my 6 electrons mark out, and I can just add it all up. So I have, I'm going to write down my iron. I've got 6, I'm going to start over here. 6 iron plus 2s. And then I'm going to write my chrome, Cr2O7 minus 2. I'm going to write my 14 H's, my hydrogen ions. And then on this side, I've got 6 Fe plus 3 plus 2 Cr plus 3 plus 7 waters. Ta-da! And that's the hardest problem on this. And that's it. Ta-da! Science is great.